All right, it's 7:01. I'm gonna get started here. Um, so I got a few new toys. This is one. It's a wireless mic that connects to a USB dongle. So this way, it doesn't matter where I stand, as long as I'm within the reception range of my wireless connection, it will still be the same volume. I checked that the voice quality is actually pretty good. It's much better than Bluetooth. It's also more reliable than Bluetooth too. So that's kind of cool. The second thing is something that you have seen already, my stylus. I lost another one at a conference, so I had to purchase this one. So now it's tethered. Yeah. My cats may still be able to get it though. They like that string. Cool. So what we'll do today is we're going to talk about the practice exam, because we're going to have our exam 2 next Tuesday. So the topics of the second exam is going to be from the double precision floating point numbers all the way to compiling code, but without subroutines. So we are going to exclude the discussion of subroutines from exam 2, but everything that's leading up to subroutines, will still be in the scope. Is that okay? All right. Okay. So what we'll do today is we'll take a look at a few examples from the past exams. They are already in a share folder. The tricky part is some of those are in X1 because it is at the end of exam 1 in the previous semester, and some of those are at the beginning of exam 2 of the previous semester. So we kind of have to look at both of those. So I'll start with the end of exam 1 from the last semester, which are related to floating point number calculations. So scrolling all the way to the end, you have access to this document, by the way. So if you scroll all the way to the end, question number 5 and question number 4, those two are the questions that can be that are relevant to what we do in this class in exam 2. So let me magnify first so that we can see what the question is asking. So question number 4 is asking, assume x is the value represented by a double. When I say a double, it means a double precision floating point number. Okay, I just decided not to write out the entire thing. So assume x is the value represented by a double that has a bit pattern of blah, 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 blah. Now, if you see 0x, what does that mean? It's a hexadecimal number, okay? So I'm using hexadecimal representation, so I don't have to write 64 individual bits. Instead, there are only 16 hexadecimal digits. There's no need to figure out x. Assume y is the value represented by a double as a bit pattern of another bit pattern. I want you to tell me what is the ratio of y divided by x. So you can definitely just figure out y and figure out x and then do the division, and that's the answer. The other way to do it is to figure out the exponents and figure out the mantissa, and then give me an explanation of why you think the ratio is a particular one. So is the question itself clear, what I'm asking? Okay. And in the previous semester, I even give people a conversion table between hexadecimal and binary. I'm hoping you don't need a table like this anymore. But if you do need a table like this, you might want to put it on your own piece of paper, just so that if I don't give you a table like this, you have your own. Okay? So once again, just like in exam 1, it is open book and open notes. You can bring anything that is either printed or handwritten prior to the test. Is that okay? All right. So how do we approach this problem? So the first thing, oops, I just scrolled all the way to the top. Let me scroll back to the end here. Page down, page down, page down, page down. Okay, there we go. So how do we look at a particular bit pattern and convert it back into the value that it is supposed to be representing? So do you guys still remember where the bits are in a double precision floating point number? Because that's the first thing you need to do, is to chop it up into the parts that you need to understand. Okay, so for that, I'm going to use the tablet. You guys are lucky because I got everything back up to work again today. Yesterday, nothing worked. So the class from yesterday basically did not get all of these tools. None of these tools worked. Yes, they can. That's right. Okay, so I'm supposed to see. I'm not seeing it. Okay. You may need to disconnect and reconnect. Okay, that's probably what I need to do. There we go. Okay, click OK. And there we go. Okay. I was also trying out different options, including a free option so that I can cast the Android screen onto the PC screen. The free option, unfortunately, didn't work too well. It's too slow. There's a lot of lag in the order of 5 to 10 seconds. So that's not very good for lecture purposes. It's good for something else, like just recording. That should be okay. All right, so what we need to do now is to remember how a double precision floating point number is structured in terms of how many bits where is responsible for what part of the value that it is supposed to be representing. Is that okay? All right, so let's say this is the most significant bit. We know a double precision floating point number has 64 bits. So can someone tell me what bit number this is corresponding to? It's bit 63 because we count from 0. Okay, so this is bit 63. And what is the purpose of bit 63? It's a sign bit. Okay, so if this bit is a 1, that means the value being represented is negative. If this bit is a 0, that means the value represented is non-negative. Okay? All I can say is non-negative because it can be 0. 0 is neither positive nor negative. And then after this, we got 11 bits, which will go from bit 62 to bit 52. What are these bits? The exponent, but it's biased. Okay? So this is the biased exponent of a double precision floating point number. And then the rest, which is pretty big, from bit 51 all the way down to bit 0, is not the mantissa. It is a part of the mantissa. This is the fractional part of the mantissa. So to be more precise, I have to say this is the fractional part of the mantissa. Okay. So is that reminding you of something that we talked about a long, long time ago? Okay, I certainly hope so. So now that we have a bit pattern that is given to us, and let me switch back to here, it's 4, 0, 2, 8, and then a whole bunch of zeros. Okay, so we'll write it down, on the tablet. 4, 0, 2, 8, and then a bunch of zeros. Okay. So we have to convert this back into individual bits because I need to know where's the sign bit, what bits go into the exponent, what bit goes into the fractional mantissa, and so on. The 4 is a 0, 1, 0, 0. The 0 is 0, 0, 0, 0. The 2 is 0, 0, 1, 0. The 8 is 1, 0, 0, 0. And then the rest are all bits of zeros. So is that still doing okay? All right, cool. So now we can isolate the individual bits, like which part is which part. So we know that this is bit 0, which means the number is non-negative. Okay. The second part is a little bit more tricky because it goes from here all the way to here. That is my biased exponent. So without even dealing with a biased part, okay? If you look at these 11 bits as an unsigned value, what is it? It's 1 followed by 10 zeros plus 1 followed by 1 0 in binary. So what do you think that is representing? What value is it representing? 1026. That is correct. Because this particular one here, having 10 zeros to the right-hand side, is 2 to the power of 10, which is 1024. This one here has 1 0 to its right-hand side. It is representing 2 to the power of 1, which we know as 2. So we have 1024 plus 2, which is 1026. Okay? But that is not our exponent. Okay? 1026 is the biased exponent. By how much is it biased? 1023. Very good. Okay, so you have to subtract the bias to get to the actual exponent. So this is basically what kind of unit we are talking about. Whatever the mantissa is, we have to multiply that to 2 to the power of 3 in this case, because 1026 minus 1023 is 3. Is that okay? All right? So now we have to work with the mantissa. The mantissa has one point being implied. So that part is never represented in a double. It is just always there. It is always assumed to be there. The rest is explicitly represented. So in this case, the rest is pretty easy because you just copy this portion here to become this portion. And of course, in this case, I chose something that is easy to work with because it is just 1.1 as a binary number, because the rest are all zeros. These are all less significant digits. So if they're zeros, I don't even need to write them. Does that make any sense? Okay. Okay, so now we got 1.1, but I have to emphasize that this 1.1 here is a base 2 number. So what value is 1.1 in base 2? We have 1, 1, and what is the other one? Sorry? Is 1/2. Very good. Okay, because the one to the left is corresponding to 2 to the power of 0. The one to the right-hand side is corresponding to 2 to the power of -1, which we know as 1/2 or 0.5. So that means 1.1 in base 2 is 1.5 in base 10. I picked up the wrong pencil. So this is 1.5 in base 10. So the value that it is representing is 1.5 in base 10 times 2 to the power of 3, which we know as 8. So 1.3 times 8 is 12. That's it. So the value represented is 12. So now you work with the other number. You just do a division, or you just write the numerator and the denominator. I will count it as correct. Is that okay? So this is one way of converting. I give you the bit pattern. You figure out the value that is being represented. Yes?
Wait, so we just have to convert the numbers? Like we don't have to reduce them or anything?
Sorry?
Like, so the question's asking for the ratio.
Yes. So you have to figure out what the other one is, and then you just say this one is over this one.
So you don't have to reduce it or anything?
You do not have to reduce it. Yep. Because that's the job of a calculator.
Yeah.
Yep. This is to test whether you understand the structure of a double precision floating point number or not. So are we doing okay so far with this stuff here? Okay. If I were to ask you this question, okay, I give you the same number here. Okay, so let me put it over here. So 4, 0, 2, 8, and then a whole bunch of zeros. And then the second number, the other number, is, let's say it's 4, 0. Okay, this is a 2. Let's make it a 1, okay? And I ask you about the ratio of x divided by y. What do you think that's going to be? Can you figure it out like right away? 40, 20, 40. Okay, so we are talking about the value represented by these bits, but you have to interpret the bits as a double precision floating point number. So you basically look at these two numbers and you ask, How are they different? They're not different by much, right? Yep. The mantissa is the same. There's no change to the fractional part of the mantissa. They are both 1.1 in terms of the mantissa in base 2. Yep. Yep. That's it. It's just twice. And the reason why we know it's twice is because we know that 401 and 402, they are all bits corresponding to the exponents. Okay? And if the exponent is off by 1, the value and everything else being the same, that means the value represented is twice. Okay? The one that has one more has twice the value of the other one. So I can make this not appear to be so easy. In other words, I can change all of these bits to be some random bits. Okay? But as long as they are the same with these two numbers, then the ratio is only controlled by the exponent and not by the fractional part of the mantissa. Yep.
So if we were showing this as the answer, would it be appropriate to say x is twice as big as y? Or
You have to explain why though.
well, yeah, obviously showing that, but
Yeah.
like writing in shorthand after.
Right. So you have to say that the value represented by the bit pattern x is twice the value represented by the value represented by y.
Would it also be appropriate to say y is half the value of x?
Say that one more time.
Would it just going backwards? Would it also be appropriate to say y is half of what x is?
Yeah, you can do that too. But since I'm looking for the ratio, then it's x to y is 2 to 1, basically.
So you'll specifically say.
Yep. You first, and then you. Yep.
Did you say that the two mantissas are the same or the two exponent parts of this?
The mantissas have to be the same in order to just use the exponent to figure out the ratio. If the mantissa or the fractional part of the mantissa are different, then they also contribute to the value that you're dealing with.
Would you just subtract the two, like the denominator mantissa from the numerator mantissa, and then just use that one mantissa, or the exponent parts, because the rules of exponents, right? You take the bottom and subtract it from the top, and then you just
Yeah, you,
that's along with the ratio for mantissas. That work?
but that's not a ratio anymore when you do a subtraction.
No, if you have like 10 to the 0 or 10 to the 1, then it's just 10 to the 1.
Exponent. So like, couldn't we just subtract top exponent from the bottom exponent? Which you could, but like we don't need to reduce, so there's no point.
No, I'm saying if that were the case, then they weren't the same.
Given the mantissas are the same, then you can use that technique. But if the mantissas are different, then the mantissas also contribute to the difference between the values. But since I'm not asking for the difference, I'm looking for the ratio, so you cannot just do a subtraction. That doesn't tell you much about the answer.
I was talking about the exponent part.
Oh, if it's just the exponent part, correct, yes. Question?
So in our answer, when we need to describe why x is twice as much, and say x is twice as much because.
So in this case, y to x is 2 to 1. Or the value represented by x to the value represented by y is 2 to 1. Any other questions about number, I cannot remember, 4, I think? Yep, there we go. So this one is okay? All right. So we're moving on to number 5, which is the opposite. So number 5 is saying, okay, I give you the value. Now you have to tell me the bit pattern that is representing this value, but using the double precision floating point number format. So it's the opposite, right? So now the question is, okay, are there any questions from back there? Yoo-hoo? No? Okay. If it's related to the class, I'm more than happy to answer.
I was just confused by we never finished it per se. You're talking about another way, but
Oh, the other way is just to look at the ratio between the exponent and also the ratio between the mantissa. But you have to be very careful with the mantissa part because the mantissa has an implicit 1 point. So it's not just the bit pattern that you see in the double itself. You have to remember there's a 1 point corresponding to it. So that's why it's a little bit tricky. Okay, that was a good question, see? All right, so question number 5. Are we ready to move on to number 5? Yes? Okay. I don't see any objections, so I'm going to move on. So number 5 is the opposite. I give you the value that we want to represent, and then you have to give me the bit pattern. But I don't want like 64 zeros and ones. I want it in hexadecimal digits. Okay, so it's exactly the opposite of question number 4. So this time we're working with negative 5.625. So let's see what that's going to look like. Okay, and we'll start a new page. So we have negative 5.625 as the value that we want to represent. So once again, we have to isolate different parts. So the first part is the easy part. What do you think is the sign? The sign bit. It's going to be a 1. Okay, very good. Easy peasy. Okay. What about the other parts? Now, there are 2 ways to look at this. One way to look at this is you have to figure out the binary representation of 5.625 and then try to normalize it so that it works. The second way to deal with this is to find the largest power of 2 that is still less than or equal to 5.625 and then establish that as your exponent and then work your way backwards, using that method. Okay, so I'll show you both ways to do this. So the first way is just to look at 5.625, and then you add, and then you say, okay, I just want to convert this into a binary number. So it's 4, which is a power of 2, plus 1, which is also a power of 2, plus 1/2, which is a power of 2, plus 0.125, which is a power of 2. This you should know already because it's in exam 1. Okay? So that means this is 100 in base 2 plus 1 in base 2 plus 0.1 in base 2 plus 0.001 in base 2. Is that making any sense? Because 4 is 2 to the power of 2. That's why we got 2 zeros here. 1 is 2 to the power of 0. That's why we have 0 zeros. Okay? 0.1 is 1 of the half, which is 2 to the power of -1. That's why it's 1 place to the right-hand side of the binary point. And then 0.125 is 1/8, which is 2 to the power of -3. And that's why it is 3 places to the right-hand side of the binary point. So there is certainly a pattern to this whole thing. So when you add up all of these, because they're already all in base 2 already, so you get 101.101 in base 2. Is that okay? The conversion from 5.625, which is in base 10, to 101.101 in base 2. Okay. So you look at this number, there's always an implicit exponent here, except the implicit exponent is 2 to the power of 0, because that's just 1. We can always multiply whatever with 1 and not change the value being represented. Is that making any sense? So what we need to do now is to look at this and go like, okay, we want to shift the binary point by 1, like so. But when you do that, what are you doing to the value of the mantissa itself? Forget about the exponent. But whenever you shift the binary point to the left by 1 place with a binary number, what are you doing to the value? You're dividing it by 2. You're halving the value. But I don't want to change the value being represented, so I better compensate by doing something with the exponent. So what do I need to do with the exponent here? 2 to the power of 1. Very good. So every time we do every time we shift the binary point to the left, we have to increment the power of 2 by 1. Okay, so that means that, right? Oops. Oh, pff. I cannot add 1 and 1. Okay, so 1 plus 1 is 2. Okay, very good. So the sanity check of this is to forget about the fractional part. Look at this, just this 1. 1 times 4 is just less than 5. Sounds right. Okay? Okay, so now that we have this format, I think we got most of the information that we need. We have the bias. Excuse me, we have the exponent, okay? But this is not the biased exponent. So if the exponent is 2, what is the biased exponent? You have to add the bias amount, which is 1023. So the biased exponent is 2 plus 1023. And by the way, this 2 is coming from this 2 here, which is 1025, okay? But 1025 is a base 10 number. I need to convert it into base 2. Is that a hard one to convert? Because it's 1024 plus 1. And 1024 is 1 followed by 10 zeros in base 2. So this is easy to convert. So the biased exponent is 1, and then 9 zeros, and then another 1 as a base 2 number. Is that making any sense? Are there any questions up to this point? Okay, so we got the sign, we got the biased exponent, and of course we also have the fractional part of the mantissa. Remember, the 1 point is not a part of the double representation. So that means that when we are all done, we have the sign being 1, we have our exponent being 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then another 1. And then we have the fractional part of the mantissa just being over here. So that's 0, 1, 1, 0, 1, and then a bunch of zeros after that. Yep. Huh? That is correct. There should be 9 zeros because we have that extra 1 on the end. So now we're still having 11 digits. So we still good? If you give me this as an answer, you'll get most of the points, but because you're not converting into a hexadecimal number, it's not getting all the points. Yep?
Why is for the exponent, should it be the last one, not the last number that's a 1?
The exponent,
For the biased exponent,
yes?
why is the last number a 1, not the second to last one a 1?
Because it's 1024 plus 1.
Oh, okay, gotcha.
Yep. Because 1 followed by 10 zeros is 1024.
Right.
So we just have to add that 1 extra 1 at the end. Yep. Okay, so now it's time to convert it into hexadecimal. So you group it by 4, okay? So 1100 is a C, 0000 is a 0, 0001 is a 1, 0110 is a 6, 1000 is an 8. Now this part is kind of tricky because I know there are a whole bunch of implicit zeros here. So when I know that it starts with 1 0 and the rest are all zeros, I just say that okay, it's 1 0 0 0 because they have to be groups of 4 individual bits. And then the rest are also zeros. How many zeros are we talking about after the 8? 11, very good, because 64 bits divided by 4 bits per hexadecimal digit means that we are expecting 16 hexadecimal digits. We handle the first 5, the most significant 5 ones, because they are non-zeros and they actually need to be converted. So the rest, which are all zeros, there will be 11 of those, because we have 44 bits that are not specified after we deal with the first 5 hexadecimal digits. Is that okay? So is this process okay? So the other way to do this, which I do not recommend, but some people can do it, is to look at 5.625 and say, okay, how do we normalize this, as a base 10 number? In other words, you look at 5.625, and then you immediately say that 5.625, you divide it by 4 first, okay? And then you do the base 2 conversion. I do not recommend this way because you have to deal with small fractions. So I personally like to work with whole numbers a little bit more than this. That's also another way to do this. Okay, so let's scratch this one. Okay, so the other way to do this is to turn 5.625 into an integer by multiplying that by some power of 2. Okay? So how do I turn 5.625 into an integer by multiplying it by the smallest power of 2?
It has to be a power of 2 such that it's 1,000 or greater?
No, it can be just 8. It can be 8. Because 8 times 5.625 is going to be an integer, it's going to be a whole number. Then I can just convert that whole number into a binary number. Then I can just shift the binary point and figure out the rest. So it all depends on how comfortable you are. Yeah, my Fitbit likes that. So it all boils down to how comfortable you are to work with fractional part as a base 2 number. If you say that I don't want to deal with that at all, then you have to convert 5.625 into an integer first, and then convert that integer into a binary number. But then you have to remember that you have to shift more times, because you start with an integer and not a fractional number. Is that making any sense? Maybe, sort of. Okay. And that's it. So do we have any questions about double precision floating point numbers? So what are you going to bring to the test to help you? I would go to Wikipedia and print out their picture. I wouldn't print out the entire thing because you wouldn't be able to find any information during the test. Instead, I'll just go with this part here. Because it is graphically telling you, which part is the fractional part of the mantissa, which part is the biased exponent. So this is not very descriptive because it just says it's the exponent. It's actually the biased exponent. And this is the sign. I would even include this in your notes because these two are equations that shows you exactly how each individual bit out of the 64 is utilized in the value that is being represented. So I would include this picture and one of these two equations or the formulae, depending on which one you feel more comfortable with. Is that okay? All right. In other words, I don't want to hear anyone during the test and go like, I don't know where the bits are or which bit is which one, during the test. Can you tell me where is the exponent and how many bits are in the exponent? I don't want to hear those questions. Because it's open book, it's open notes. You can bring all that stuff with you. So are we doing okay so far with this? Cool? All right. So let me go to another question. Okay, so let's go to exam 2. Now, exam 2 from last semester is also different from this semester because we have not covered anything about functions or subroutines. And this particular test has a lot of those questions. So the only question that I can really ask is, okay, scrolling down to here, is this one. Okay, so let's read the question a little bit first, and then we'll try to figure out the answer. So the question is saying that I am adding a new opcode. Okay, so you don't have to add the new opcode. I'm adding a new opcode. And I'm telling you that with this new opcode, slice 0 of the microcode is this particular bit pattern, and slice 1 is this particular bit pattern. I want you to tell me what the instruction is actually going to do. So describe the new instruction based on the microcode that is already presented to you. So how would you answer that question? What do you need to bring to the test to answer this question? The diagrams, very good. Okay, so we start with that. So there are several diagrams, and I prepared those diagrams for you already. In other words, you just have to go to the share folder. Okay, so let's go to the share folder first. cisp310 shared. It's under the processor subfolder. So you go to the processor subfolder, I just made it today, so it's called PDFs. And guess what it has? PDFs. And the PDFs are corresponding to the names of the components that they are the PDFs of. So one is, so I would print out all three, okay? Particularly, the processor one is going to be really extra, useful, because you cannot answer that question unless you know, where the tunnels are, okay? So this is going to be useful during the test. If you have eyesight like mine, you might want to print it on a larger piece of paper. My eyesight is actually not that bad. It's just that I cannot focus closely. So I have to wear my extra glasses or take off my glasses in order to read it. But most of you are much younger than I am, so you don't have that problem yet. You will, if you're lucky. And LASIK won't fix it either. Do you guys know why? The problem with aging has to do with the lens getting stiff and it's not flexible anymore. So the problem is not that my lens itself is faulty, it is just that it cannot change its shape. So I cannot change my focus anymore. So I have to rely on my glasses, bifocal, and also clip-on stuff to change the actual focus of what I'm looking at. But other than that, my lens is fine. It's just not flexible anymore. Okay, so getting back to this. So when you look into this, or when you look into Logisim, okay, which I also have loaded, the names of these tunnels are corresponding to the names of that particular spreadsheet already, the table. So let's go back and forth between the table in the test itself and also that thing. So with the exception of microcode pointer select, which is not named in the diagram, everything else are just as they are named in the diagram. This one here, microcode pointer select, is corresponding to a line that has no name, that has no tunnel corresponding to it. It's corresponding to this particular line here. It has no name because it comes straight from the splitter, and because it's so close to the ROM, I decided that, let's not name it. Okay? So if you want to make it more complete, you can always just attach a text label. So just use the text tool here, put it somewhere close, and say this is my Ucode pointer select. Okay? And there you have it. You can always annotate your own PDF. Okay? Do you guys know how to do annotation on a PDF? Yes? No? What kind of program do you use for that? And blah, 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 blah. No? Huh? Adobe? Okay, Adobe can do that. Yes, that works too. But if you have a lot of annotation, a lot of typing, and stuff like that, I can point you to an open source program that can do it. It's called Xournal, Xournal. And I believe it is multi-platform. It's not Linux only. So it's really kind of cool because it can open any PDF, and you can just annotate on the PDF that you open. It doesn't require a tablet, doesn't require anything that you need to spend money on. There's definitely a Windows version. So for those of you who are using Windows, there's one port for Windows. It's a great tool, okay? For any class that they supply a PDF document, you can use this to annotate the PDF document itself. If you go to a website, okay, and you want to annotate content of a website, print the web page to a PDF first, then use Xournal to open the PDF, then you can annotate the web page as well. So it's a great tool, not only for this class, but I'm just introducing that to you. And the best thing is it's free. You don't have to pay for it. And it works fairly well. I use it a lot. So is that okay? All right. Oh, one more thing. What if in the test you suddenly forget how a multiplexer works? what are you going to do? You walk up to me and go like, Tack, I completely forgot what a multiplexer is. What is this little pin here that has a gray dot next to it? I'm not going to answer that question. Why not? Because you can print your own manual, right? Okay. Do you guys remember how to do it? Okay. All right, cool. So there are all of these tools that can help you to prepare for the exam. So now the question is, okay, getting back to the actual question here. So getting back to the actual question, which is this one, what do you do when you look at this type of question with a diagram? What do you do to figure out what it's going to do? What is the first thing that you're going to look at? Sorry? Find the names. Okay, so you want to do that before the test. In other words, you want to be, okay, I take part of that back. You want to get familiarized with a diagram before the test, okay? Just because you have the diagram and the map and it has every information that you need to know to answer the question doesn't mean you can do it in time. That is the issue, okay? So you want to get familiarized with the diagram beforehand so that you know approximately, oh, I know the piece is over here. I know the ALU is over here. I know the registers are over here. I know the tunnels are over here, over here, over here. So that way, during the test, you're not going to spend too much time to look for a particular tunnel and how it is connected to the components. That is what you need to do ahead of time. Okay. So with this one, you know, we have microcode pointer select being a 1. What does that do? Okay, so we switch back to the picture. And this is microcode pointer select. And it's connected to this select pin of a multiplexer. So all that does is to say that we're going to use input 1 of this multiplexer to update the microcode pointer. And what does that mean in return? Exactly, it's just going to increment. Okay? In the next falling edge, the microcode pointer is going to increment. That's all it's done. That's all it's going to say. Which basically means, you know, whatever the microcode is, when it's done, we just move on to the next one. That's all it's going to say. Okay. In other words, most slices is going to have this, except for the last one. What about PCEN? What do you think that does? It's program counter enable, which means we are going to update the program counter. It may not be incremented, okay? It can be updated in some other way, but we are going to change it. Is that okay? So if it is a 0, like in the second slide, that means I don't have to pay attention to PC mux and a few other things because the program counter is not affected. On the other hand, if the program counter is going to be updated, I need to know how PC mux is configured because that ultimately affects how the program counter is going to be updated. Is that okay? So now we look up the diagram and we look up the tunnel name called PCEN. One is over here, but that's just the name of one end of the tunnel. The other end of the tunnel is over here. So this is PCEN, and you can see how it connects to the enable pin of the program counter as a register. So that's why we know when PCEN is a 1, the program counter is going to be updated. So now the question is, how is it going to be updated? The program counter is going to be updated by the output of this multiplexer. Okay? So then you need to know, oh, I know PC mux is going to control, you know, how this multiplexer is selecting from its input. So now you have to look up PC mux and go like, okay, how is PC mux, you know, going? Is it going to be a 0 or is it going to be a 1? Because that really needs to, that's what you need to know to determine which input is going to be the output of this multiplexer. But PC mux is not a part of the ROM. The ROM output does not have a pin called PC mux. Instead, it has PC mux, or the multiplexer of a multiplexer. So PC mux connects to this, you know, kind of bigger multiplexer, and I think the table says that PC mux is going to be a 7. So what is the result or what is the effect of PC mux being 7? What is going to be the output of this multiplexer? In other words, what is going to be PC mux? It's going to be a constant of 1, exactly, because when PC mux is 7, that means we are selecting input 7 to become the output. Input 7 is connected to a constant of 1. It doesn't change at all. So that means PC mux is guaranteed to be a 1 when PC mux is a 7. Okay. So now we go back to this part of the circuitry. So now we know PC mux is a 1, which means we have to track down this particular connection. It doesn't go very far. It just goes to another multiplexer. So now we have to figure out how are we selecting in this particular multiplexer. What I click is not the actual answer, by the way, because I'm not executing that particular instruction. So you look at this particular select pin. It is coming from an AND gate. Okay? One part of the AND gate, or one input of the AND gate, is connected to PC mux, which we know is a 1 already, right? But because it's an AND gate, having one side being a 1 doesn't mean the output is going to be a 1 or a 0. We have to look at the other one. So the other one is called register output 0 enable. That turns out to be one of the things that is specified in the table. So you look up the table, and you look up R register output 0 select. Register output 1 select. Sorry. Is that? Register enable, not select. Enable. Okay, there we go. So that is a 0. Okay? So when you go back to the diagram, then we know that register output 0 enable is a 0, but this is negated. This input is negated, which means now we have a 1 from here, and this input to the AND gate is a 1 as well because it's a negated 0. So the output of the AND gate is going to be a 1. So that means, in return, we're going to select input 1 of this multiplexer to connect to the program counter eventually. Is that okay? So now we have to track that wire down. This particular wire goes to a lot of places, okay? And eventually you will see that it goes to RAM. It goes to the D port of RAM, which means it is actually connected to the content of a particular location that is addressed in the RAM. Okay, so now we know the RAM component can be important. So the next thing we do is we look up the control signal going to the RAM, and we say, are we using RAM at all? Yep, RAM select is a 1. What are we doing to RAM? Are we reading or are we writing to RAM? RAM load is a 1. That means we are reading from RAM. So that means the RAM is driving the D port. The RAM is basically supplying content that eventually is used to update the program counter. But that leads to another question. Who is going to specify what location we should be looking into in RAM? It's whatever data bus or the data port is specifying, right? So now you track this guy down and go like, okay, who is specifying what is on the address port? The address port comes from a multiplexer. That particular multiplexer is controlled or selected by address mux. Okay, so we go back to the table. We look up address mux. It is a 0. So that means we are using input 0 to connect to the address port of RAM. And where is that coming from? It's coming from the register bank. To be more specific, it is going through a demultiplexer into the RAM, into the register bank. It's coming from output 1 of the register bank. So that means some register in the register bank is used to specify what location in RAM we're reading. And then the content that we are reading from RAM in return is used to update the program counter. So that leads to another question. Which register in the register bank is output 1 at that time? So when you look at the the register bank itself, there's a register output 1 select, okay, which specifies which register are we using as output 1 of the register bank. Go back to the table. Register output 1 select is 3. So which register are we using? Register D. Very good. So now we complete the entire path. Register D of the register bank is used to specify what location in RAM is used to update the program counter. That's the first slice.
Wait, can you say that one more time?
This is why I'm streaming, so that you can actually just kind of go back and TiVo the whole thing. So register D of the register bank is connected to the address port of RAM, which selects what location. The content of that location of RAM is used to update the program counter.
So whatever D points to in RAM is going to be the new value stored in the program counter.
Exactly, that is correct. Whatever content the D points to is going to be used to update the program counter. That is correct. So now the answer, what you can either spell out, in a sentence, or you can also just, specify. I don't want to show my actual answer here because the second slice, the answer to the second slice is right there as well. So I'm going to do it over here. Okay. So the first one, you can just say that your PC, whatever PC is updated by whatever D points to. So I would just use this method to indicate the result of the operation. Is that making any sense? Okay. There's a second slice. So with the second slice, what are you going to do? What is the general strategy do you think is happening here? You have to identify what components are active. In other words, pay attention to the enable first. Okay, the select, the enable, those are the important stuff to focus on first. So when you look at the second slice or slice 1, the program counter is not even enabled. I'm not going to pay attention to PC mux because I can specify anything as PC mux. It's not going to do a single thing. What about the ALU on slice 1? The ALU enable is a 1. That means I am using the ALU for that operation. So that means I need to know what the ALU is doing. What the ALU is going to do is controlled by ALU op, which is kind of its own select. 0 means we're adding. Okay? How do we know that? How do we know that 0 is adding, 1 is subtracting, and so on and so forth? Yep, exactly. That's why you need the schematic of the ALU itself so that you can tell which operation, what number is corresponding to which thing inside the ALU. Is that okay? That's important. So we know that 0 is adding. So now the question is, what are we adding? That's the question. So when you look at the schematic, this is the ALU. We have to figure out what is going in 1 and what is going into in 2. So we need to figure out what those things are connected to. In 1 is a little bit easier because in 1 has to come from this particular demultiplexer. There's no other way that it can come from. And this particular demultiplexer is out 0 of the register bank. So that means I need to know who is specifying output 0 of the register bank. Switching back to this table here, register output 0 select is 3. So which register is that corresponding to? Register D. So register D is going to input 0, or the first input of the ALU. Now we need to look at the second one. Okay? The second one is the complicated one because the second one comes from a multiplexer. So now you need to figure out what is the selection bit of this particular multiplexer. That one is a little bit complex because it's going to FC, and FC is the NAND between ALU-EN, which we know is a 1 already, and RO1 demux. So now we need to track down register output 1 demultiplexer and see what it is. Okay, we are talking about this line here. So you go back to the table, you look up register output 1 demultiplexer, and register output 1 demultiplexer is a 0. Okay, so you go back here. 1 is 0, 1 is a 1, but this is a NAND gate. So what is going to be the output? The output is going to be a 1, because if it is a NAND gate, if at least one input is a 0, the output is going to be a 1. Okay, cool. So we know that we are using input 1 of this multiplexer to feed to in2. And input 1 of this multiplexer is just a constant of 1. In other words, we know at this point that in1 is connected to register D. We know that in2 is connected to the constant of 1, and the operation that we're performing is adding. In other words, we are just adding 1 to register D. But now the question is, when we're done adding, is it going to go back to be stored somewhere? If it is going back to store somewhere, who is storing that result? Okay, so now you need to track down this wire, which is the output of the ALU. It doesn't go very far. It goes into this multiplexer. So now you have to look into RIMUX, register input multiplexer, and make sure that it is 1. I have a strong suspicion it's going to be a 1, but we have to double check. Register input multiplexer indeed has a value of 1. So that means it's going to go into here, which means it's going to be used to update one of the registers in the register bank. Okay? But in order to know which one is going to be updating, and also whether it's going to be updating any of the register, let's double check and make sure that RIEN, or register input enable, is also a 1. Register input enable is also a 1. We are in fact going to update a register in the register bank. And the register that is selected to be updated is register 3. And that turns out to be register D. So register D equals to register D plus 1. That's basically what this operation is. So that means, when in your answer, the second slice, okay, come on, read my fingerprint. There we go. Okay. So that means in your answer, the second slice is going to do something like this. Or if you prefer, D plus equal 1, plus plus D, they're all equivalent. D plus plus works too, because we are not actually using the result of the expression, so the side effect is the same. Is that okay? But did you guys understand the process of how to answer that question? What is involved in the process? So if that is going to be one of the questions that I will be asking, how do you prepare for that question? How do you make sure that you can answer that question within a reasonable amount of time? See, the question is not whether you can answer the question or not. It is about how long does it take for you to answer the question. So what can you possibly do to reduce that amount of time? That is up to you guys to decide. Is that okay? All right, cool. All right, so that's another question that I can ask in exam 2. The other questions in the practice test does not really apply. Let me show you why they do not apply. It has to do with all of those involve subroutines, and we have not talked about subroutines. Okay? Yep.
The rest of the questions of my exam involve a lot of subroutines. So far, you've gone over just conversion from hexadecimal digits and the ratios.
Yep.
Navigating through the processor. Is that the basis of the question?
Yep. So instead of having subroutines, I can still ask you questions about coding, except everything will have to be in registers and memory. Absolutely.
Give us a brief example, I guess.
Yes, I think I still have that document open. Let me see if I still have it here. Nope, not that one. No, that is not what I'm looking for. I think it's this one. Yep, there we go. So I can give you code like this. Okay. Okay. So it can go in either direction. I can give you code like this and say that A, B, C, D are registers, and then you have to give me the assembly code that accomplishes exactly that. So that's one type of question. Or alternatively, I can write the assembly code and then ask you to reverse it back to C code. So it's going to be something like this. So there are two programs here, by the way. There's this program, which is division, and there's also this program which initializes locations in memory. I may not be asking about memory locations because we haven't really been using a lot of instructions to deal with memory locations. But something like this over here, which is just doing calculations using the registers, is certainly within the scope that I can be asking in exam 2. So let's go ahead and work on this one. Okay, so if I want to convert this code into assembly code, what is it going to look like? You guys can start with the first one, the first line. Is that the? Yep. Okay.
Load I into C0.
Okay. And then the while gets it's a little bit tricky. Okay. Begin loop is as a label is a good idea. And if you have a begin, I'm expecting an end as well. Okay. Now the only part that's kind of difficult is you cannot type like this when you are writing on a piece of paper. So you probably have to leave some space in between or do something else to do it this way. Okay, so when am I getting out of the loop? When A is less than B. So if I don't tell you whether A and B are signed or not, then you have to ask me during the test. Okay? But what if I tell you that A and B are unsigned? Then what do we do to get out of the loop when A is less than B? A is a register, B is a register.
CMP.
Okay, we always start with CMP because without a compare, we don't know the ordering. Okay, but after the compare, we have flags already set, right, or cleared, changed anyway. Which flag should we use here to perform a conditional branch? J something I to end loop. Okay, so the question is, what flag should I look at when this is an unsigned comparison? The carry flag, which is also known as the borrow flag. Okay, so there are two flags, okay, that are used to specify whether something is less than or not. One is the C flag or the carry flag. The other one is the L flag, which is the quote-unquote less than flag. How are they different? What is the definition of the borrow flag? Okay, so let's revisit a little bit, okay? This is how we study, okay? We basically have to revisit all that stuff. So the carry flag, which is also known as the borrow flag, they're basically the same thing. Yep.
I was going to say how they're different.
Okay.
Isn't it unsigned versus signed?
Yes, it has to do with signed versus unsigned, but that eventually boils down to how we interpret the bits. Okay? So the carry bit in the context of a subtraction is what? How do we define that? We should know this already. Yep, so it's the borrow function of x 7y7, the most significant bit of the two numbers, x being the minuend and y being the subtrahend. But there's an or, right? Oh, okay. Okay, there we go. Much better. Okay. So the borrow flag, the overall borrow flag as the output is the disjunction between the borrow of the minuend bit 7 and the subtrahend bit 7. Okay? In other words, if 0 is x7 and 1 is y7, we guarantee a borrow already. But there's also something else. It is also, it can also be coming from the borrow between what we call Q7, which is the result of X7 minus Y7, and the borrow bit of bit 7, which is calculated by some other bits. So that's the bottom line. But why is this indicating that X is less than Y when C is a 1? That goes all the way back to some discussion that we had much earlier when we talk about binary subtraction. So if you're not clear why the borrow flag indicates whether the minuend is less than the subtrahend interpreted unsigned, you have to go back to that module and reread that. Is that okay? What about the overflow flag? How is that defined? I mean the L flag. The L flag is defined as the sign flag exclusive OR with the overflow flag. Okay? And why do you think the L flag is reflecting whether the minuend is less than the subtrahend, but interpreted in a signed way? Because most of the time, the sign flag on its own should tell us whether a number, the minuend, is less than the subtrahend. Because when you subtract a number from another number, if the result is negative, that's pretty clear that the minuend is less than the subtrahend, right? Except sometimes there's not enough bits to represent the result, the difference. So if there are not enough bits to represent the result, we have an overflow situation. That's why we have the overflow flag. The overflow flag being a 1 means that we ran out of bits, which also means the sign flag is incorrect. Is that okay? So when the overflow flag is a 1 and the sign flag is a 0, it means the sign flag should have been a 1, which means the minuend is less than the subtrahend. So that's why we look at the exclusive OR. On the other hand, if the sign flag is a 1, but the overflow flag is a 0, that means we did not have an overflow situation. The sign flag is correct to begin with, which also means the minuend is less than the subtrahend. Yep?
And also, rewrite this to not S and O or S and
Yes. You can also look at it that way, but it still boils down to those two situations. Yep. But it does make it more clear, because when you look at it as not sign and O, or sign and not O, that makes it more clear when the L flag is going to be a 1. Because one of those two conjunctions can make the L flag being a 1. Okay. So getting back to our example here, which one should we use? JCI. Very good. So if someone put in JLI instead of JCI, some points will be taken, because it indicates that there's not sufficient understanding of how these two flags are different, when to use which one. Okay. What do we do next? Okay. This is essentially saying if A is less than B, let's get out. Okay. So if we're not getting out, what are we supposed to do? Subtract AB, which means we are subtracting B from A, and then store the result back into A. And then what do we do? Increment C. Okay, if someone turns in this solution, I will still take off some points, because this is a one-shot thing. Okay, we are turning a loop into a conditional statement. It's not a conditional statement. What do we need to do now? Go all the way back to the beginning. JMP. Now, if someone gives me this, I would also ding some points, because it is not JMP, it is JMPI. Very good. There we go. So now we have the code. So it can go in either direction. I can give you the assembly code and then ask you to reverse it back into the C code, or I can give you the C code and you have to translate it into assembly code. Yes?
What about halt?
The halt instruction?
Yeah.
What about it?
Do we need put halt or something like
No, because I'm just looking at this piece of code out of context. So there may be some additional code that we need to execute. So there's no need to specify the halt instruction in this case.
Same reason why we're not doing anything like returning values to A and B instead.
Correct. Because there can be something else that are setting the values of A and B. So that's why we just focus on whatever is given here in C code and just convert that into assembly. There's no need to assume that, oh, do we have any additional code? Who knows? Do we have any code before this that will actually set the values of registers A and B? Who knows?
If we did have halt, would that be marked wrong?
No, I'm not going to mark that wrong. I'll just ignore that. It depends on where your halt instruction is. If someone says, I just want to be safe and put a halt instruction, I'm going to put it here. Then I'll just go like, I'm just going to be big 0 here. Because that clearly indicates that that person did not understand, the structure of a program by putting a halt instruction before everything else. On the other hand, if the halt instruction goes here, then they go like, okay, that's fine, not a big deal, because I didn't say whether there are additional code after this or not, so it's all cool. Yep.
For instance, because we're on the subject of halt, how would you just state it as return 0 if we're converting it from C, or what would indicate us to add the halt instruction?
If I just give you a piece of code like this,
What would you add to the end?
you don't need to put a halt instruction. There's no indication whatsoever that you need to put a halt instruction here.
This one, yeah, but like to make it so if for it to include a halt instruction.
What is the indication?
Yeah.
I don't think you will have any questions that requires the use of a halt instruction. The only reason why we have the halt instruction in our programs up to this point is so that when you run the program in Logisim, it stops at a certain place. It doesn't just go crazy after that. But since in the exam, you're not going to use Logisim, it doesn't really make sense anymore. There's no need to use a halt instruction. Yep. Question?
I was looking at previous past exam 1.
Uh-huh.
There was quite a few D flip-flop models on there. Is there going to be anything like that on this exam as well?
I don't think I'm going to put any D flip-flop questions in it. Yep. So the entire module that talks about the D flip-flop is good for information purposes, but it's not going to be a topic in the exam. Yep.
Nothing about like definite states or anything like that?
What do you mean by definite states?
It's like kind of on the D flip-flop one. Like one of your questions has a D flip-flop. And it
Uh-huh.
says, given that you know...
Oh, okay. Yeah, not in this exam.
No.
Not in this exam. The only takeaway from that particular module is how to use a register as a module, as a component. So what is the enable line? What does it do? What is the clock line? What does it do? What is the reset line? What does it do? Basically, how do you use a register? That is important. So you look at a register as a single component, and you basically say, okay, how do we use it as a component? But you don't need to go into the component and figure out how it gets the job done. All right. So any other questions? I can ask some questions in the form of, I give you the assembly code, but I will ask you to fix problems. Okay, so I can mess up a program that is otherwise perfectly okay. For instance, I can take out this line. You have to say that, oh, it's missing an unconditional branch back to the beginning. I can give you something like this, and you go like, no, this is not JC, it's supposed to be JCI. Okay, or I can give you something like this. It's supposed to be LDI and not LD. Okay. That sort of thing. Or I can also be tricky and reverse the order of the registers in a compare. And you have to say, we are not going to exit the loop when B is less than A. We're going to exit the loop when A is less than B. So those two operands are reversed. Is that okay? Or there are tons of ways to make questions. I can give you a JLI, even though I spell out in the C code that those things are supposed to be unsigned. So you should be able to spot that I'm using the wrong flag. Is that okay? So I can ask that kind of question. I give you the code that is flawed, and you have to find out where the flaws are. Yep.
Would you give us a code and say that it's flawed, but it's really not? Like, find the problems, but it's actually fine.
Probably not. If I say that the code is flawed, it is going to be flawed. But I will not tell you ahead of time how many flaws there are in the code. So you basically have to find as many as you can. Yep.
Can you give us assembly code and tell us to make it in top, like turn it in top code?
Into binary opcode? No, I'm not going to ask those questions. Yep.
For instances where we are looking for an error, are you also going to give us the correct C version of it so that way we can, because it might.
Yes, I will give you the C version. Yep, yep, exactly. Because otherwise you cannot know whether the original intent of the code is to have when A is less than B, get out, or when B is less than A, let's get out. So I will give you the C code, give you the flawed assembly code, and then you have to fix the assembly code so that it gets the job done. But without rewriting the entire thing, because I know some of you guys are going like, oh, I can just rewrite the whole thing. It's faster than finding the flaws. Yep.
In the designing C structures module,
Say that one more time.
in the designing C structures module, where
Mm-hmm.
you were converting assembly to like C code,
Mm-hmm.
there was a pretty specific process you went through, and then like there were the intermediate steps of writing like go to and like doing that and everything.
Right.
Are we expected to follow exactly that process?
No, that is more of a guideline. Like, if you want to have if this is the first time you do it and you just want a mechanical, structured way to do it, that's what that module is about. But when you're already kind of used to it and you understand, what the conditional branch instructions and how nesting works, then you can just go ahead and do it in your own way. But for people who cannot just come up with their own way, like just intuitively, it gives those people a mechanical method to convert from C code to assembly code in a very step-by-step manner. Yep. So you do not have to follow that structure entirely, but your code still has to work correctly. That's the bottom line. Yep. All right. So do we have any further questions about exam 2? Yes.
Should we expect like nested loops?
Yes, things can nest. That is correct. So I can give you a conditional statement inside a loop, or a loop inside a conditional statement. So that can happen. So I'm not going to rule out nesting. Any other questions? Yep.
So like the three types of concepts we can expect for the test is like tracing through the tactoid processor,
Mm-hmm.
the double fold precision, and the convert code memory questions.
Yep.
Like, we can-
Okay, so let me kind of summarize what I want to assess, in exam 2. How well you understand double precision floating point numbers, okay? Converting one way to the other one and then back, but ultimately it depends on, do you understand the representation, okay? So that's one. Second one is, do you understand the processor architecture, okay? How are all of these components connected? How are the multiplexers and demultiplexers work together? What is a register? What orchestrates the entire thing to get things done? Okay, so that's another thing. And then the third one is, how well do you understand the assembly instructions? Okay, what is this particular instruction? What does it do? And how do you use those instructions to make programs to accomplish a certain thing? Okay, and that's basically the bottom line of what I'm trying to assess. Question? Yep.
Yeah, I was just curious, if you do nest different control structures, are you going to indent them, or should we just expect like a big line of statements?
I have not made up my mind yet with that one. So with that one, if I do not give you indentation, how would you figure out the nesting of those things? Well, okay, so let me rephrase the question. How do you read a program to figure out the nesting of a particular piece of code? Hmm? Curly braces? Well, yeah, but the question is, I give you the assembly code that is representing a nested control structure. So how do you reverse that and figure out, oh, this is the inner blah, 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 this is the outer blah, blah, blah. Yep,
You start at the highest point, and that's the outermost point.
yep. There are only three control structures that we have talked about. It's a while loop, if then else statement, and a do while loop, right? So when you look at a while loop, what indicates the beginning and the end of a while loop? The labels, right? So the unconditional branch back to the first label and the conditional branch to the end label, that controls the scope of the loop. When you look at a conditional statement, how do you know the scope of the conditional statement? There's the branch to the else part, right? But then the then branch also has an unconditional branch to the end of the entire conditional statement. So once again, you can look at the conditional branch and also where the label is located to define the scope of that particular control structure. So if I don't give you indentation, you can still figure out the nesting by analyzing the jumps and the labels. So basically pay attention to the jumps and the labels corresponding to the jumps. That usually will give you a clue of the scope. I guarantee, okay, this I can promise, I won't give you spaghetti code. I will give you code that is well structured to begin with, and as a result, the assembly code reflects the structure. I'm not going to give you assembly code where you have a branch from inside a conditional statement of a loop into another loop, another conditional statement where the label is, okay? So that is not going to happen. Is that okay? That was a good question. But the answer is I haven't made up my mind yet. Yep. I have not made up my mind either because it depends on the complexity of the question. Because you can see, if I make this really simple, it doesn't take much time. If I give you something in the order of like the absolute value code, it doesn't take much time. On the other hand, if I give you something like a conditional statement that is nested inside a loop, that's going to take more time. So I cannot give you the number of questions. I'm thinking that I want to give you shorter, smaller questions, but more of those, instead of giving you like 3 gigantic questions. Yep.
Probably the best way to study would be just like make like little tiny C programs and then just convert them.
Yep.
Like,
Yep. Exactly. That's a good, and also you can test those things too, because you can go through Logisim to test. Yep. So if you study and you have any questions, bring your questions on Thursday. That's the reason why I scheduled the exam to be 1 week from the practice exam, so that you guys have a chance to study and bring questions back to me. You have one chance to do it before the actual exam. All right, so I'm going to shut down here and go to the lab.